Hello Form 3s, welcome to today's lesson. Hope everyone is fine, and let me hope that you are keeping the SOPs. Take care, be safe. In today's lesson, we are going to be continuing with our matrices, but in the previous lesson, we ended with a subtopic, adjunct of a matrix. Yes, we looked at an example, but if people did not understand well how an adjunct is obtained, we are looking at an example to remind those ones who have forgotten. Matrix M has elements -2, 4, -3, 5, and we are required to find the adjunct of matrix M. So what we do, we interchange elements in the leading diagonal. So the elements in the leading diagonal has elements -2 and 5. That is the leading diagonal, all the major diagonal. So we interchange those elements there, meaning 5 swaps and goes to the position of -2. -2 comes to a position of 5. Then we change the signs of elements in the minor diagonal. That's why you are seeing a 4 becomes negative and a -3 becomes a positive. So that's why we're saying we get an adjunct of a matrix by interchanging elements in the major diagonal and signs of elements in the minor diagonal. So in today's subtopic, we are interested in getting determinant of a matrix. In simple terms, a determinant is a magnitude. So if we are to determine a determinant of a matrix, we get product of elements in the major diagonal minus product of elements in the minor diagonal. So that's why we are having 2 times 4, those in the major diagonal, and we subtract off the product of -3, 1, those ones in the minor diagonal. So the product of the major gives us 8 and product of the minor gives us -3. But remember, we are taking their difference. So we have 8 minus -3 giving us 11. Okay. In general, if A matrix is equal to A, B, C, and D, det A, or if we don't write det A, we write magnitude of the determinant, magnitude of the matrix. So symbols, those straight lines are showing magnitude. So they represent determinant. If I don't write the word, I can use those symbols to help us find the determinant. So if we are to get the determinant of A, we shall have AD minus BC. An example there, we have 1, -3, -2, 6. If we are to get the determinant of that matrix G, we have 1 times 6 minus, then we have -2 times -3. We end up having 6 minus 6, which gives us a 0. So a matrix with non-zero elements, but whose determinant is 0, is said to be a singular matrix. And such matrices don't have inverse. So we have said the matrices with 0 determinant don't have an inverse. What is an inverse? So if we have a matrix, the reverse of that matrix would be the inverse of a matrix. So an inverse of a matrix is denoted by, if A is a matrix, its inverse is denoted by A power negative 1. But that inverse, by definition, is equal to 1 over the determinant of A multiplying the adjunct. So if A is equal to A, B, C, and D, det A is AD minus BC. Then the adjunct is interchange elements in the major diagonal, which is D and A, then change the signs of the minor diagonal, negative C, negative B. So our inverse will be 1 over the determinant of A, which is AD minus BC, multiplying D, negative B, negative C, A. Okay, let's take an example. If we have matrix P equaling to 1, 2, 3, 4, we are required to find the inverse of P. So we shall get the determinant, which is 4 minus 6, equaling to negative 2. The adjunct is 4, negative 2, negative 3, 1. So our inverse is going to be 1 over the determinant, 1 over negative 2, into the adjunct. But we make sure that the fraction is entered inside the bracket. So each of those elements is multiplied by 1 over negative 2, giving us 4 over negative 2, negative 2 over negative 2, negative 3 over negative 2, 1 over negative 2, giving us negative 2, 1, 1.5, negative 0.5. Now, there are some facts we need to find out. 1. What happens when we multiply a matrix with its inverse? The multiplication has been done there, and we are seeing we come up with an identity matrix which is unity. 2. In part 2, we are having the inverse, this time multiplying the matrix. Still, we come up with the same thing, which is an identity matrix, which is unity. Therefore, we conclude and say an inverse of a matrix multiplying its inverse is the same as an inverse multiplying a matrix and is equal to a unity matrix. Exercise on the matrices, lesson 3. Please attempt those numbers, and in case they are not clear in the video, or go to the e-learning library, print out the questions using that link. Please. We love you. Keep on sanitizing.